So today, last week we were able to hear in some detail some observational information about what stars do to their immediate environment in star formation regions. And this week we are going to zoom back into the stars themselves and look at observational traces of activity in stars. And today's speaker is a world-leading expert in this is Beate Stelzer from the University of Tuebingen, and I'd like to invite Wolfgang to make the formal introduction. Wolfgang.
Okay, thanks. Yeah. So, brief introduction to Beate. She actually started her scientific career in Tübingen with a diploma thesis on Hercules X1 RXTE observations, and then she moved to the Munich area. She worked at the Max Planck Institute for Extraterrestrial Physics and the LMU on ROSAT data X-ray observations of a star-forming region, the Taurus-Auriga-Perseus star-forming region. After finishing her PhD there, she then decided to move to Italy and on a Marie Curie fellowship started working at INAF and in particular at the observatory in Palermo. And she stayed there for quite a while. In 2005, she became a research scientist in Palermo. She still holds this position. However, in 2017, she also moved back to Germany and took up professorship at the University of Tübingen, where she also still is, of course. And today, we are very curious to hear about active life of stars by. Thanks.
Okay, hello everybody. I think the microphone is working, if I don't see any message over there. Let me thank first to you folks who have invited me and have given me incredible 2 days here. I got around a lot in basically all the astronomy institutes in Heidelberg, and it's quite impressive to see what quantity and quality of research you're carrying out in astrophysics here. Okay, so the topic of my talk is the active lives of stars probed with space missions. I'm currently holding that professorship for observational space astronomy at the University of Tübingen, and I've decided on this topic, which is where I've been most active during the last years, and I'm building my new group. The missions that we're using are shown here on my title slide, and I will lose a few more words for each of them later as they come along during the observations that I'm going to show you. But let me first give you a general introduction. Maybe there's some students around who are not so familiar with magnetic activity. So let's start thinking, what is an active star? If you ask this question, one star comes up immediately. That is, of course, our sun. These are stunning images, or actually a moving taken by the Solar Dynamics Observatory. I show you in a moment the movie, if it's working, showing the main layers of the solar atmosphere. It's actually, unfortunately, not in order. This is the innermost, the photosphere, then comes the chromosphere, and on top we have the corona. And what you can see in this movie, in general in the pictures, is that 3 things basically. First of all, the solar atmosphere is not homogeneous spatially. Secondly, there's a lot of temporal variability. And third, if you look at what's happening in the different layers of the atmosphere, it's correlated with each other. So the question is now, is our sun a typical star, and what other stars can be active? To do that, we look at the HR diagram, and we need this kind of structure, just schematically here, with the 3 atmospheric layers, and this turns out to be possible only in the right half, in the cool half of the HR diagram. So only the photospherically cooled stars can have hot upper layers in the atmosphere, chromosphere, and corona. Why is this? Now this goes back to the interior structure of the stars. If you look at a rough sketch here, if you go along the spectral type or temperature sequence, you have at a certain point a change from inner convective to outer radiative to the opposite. And what you actually need in order to drive activity is that the outer portion of the interior that connects to the atmosphere is convective. The reason for that lies in the stellar dynamo, which is the mechanism that produces the magnetic field of the star. And it's to be taken into account here that the magnetic field is generated inside the star, as is shown in this sketch. If you start out with such a poloidal field, then due to the rotation of the star, the field will get wound up around the star. It will convert into a toroidal shape, and then you have buoyancy in the convective outer layer, which brings the magnetic field to the surface. And only if you have the magnetic field on the surface, you can drive magnetic activity. So this is actually half of a stellar activity cycle. The other half would be to convert this back into a poloidal field, and this drives the cycle on the sun, to which will be coming in a moment. So in fact, variability is a key characteristic of magnetic activity in the sun and other stars. And I show you here again, as a part of introduction, the solar cycle across different wavelengths, which trace different layers of the solar atmosphere. From the top, we have again the photosphere, the chromosphere, and the corona. And you can see here the main tracers for this activity, and you can see that they are cyclic with the same period. The tracer for the photosphere are sunspots that have been monitored over hundreds of years for the sun. In the chromosphere, you see broad emission lines in the optical or ultraviolet, especially the calcium H and K lines, which has been, for which the so-called S index has been defined. It basically measures the emission line strength with respect to the local continuum in the spectrum. And in the corona, the plasma is so hot that you have X-ray luminosity. One thing I'm pointing out here is that for the sun, the cycle in X-ray luminosity is rather large. I think I may not have time to get into the cycles of stars later on, but it turns out that the cycle amplitudes for stars are much lower than for the sun. So please keep in mind, for the sun, the X-ray cycle has an amplitude of at least a factor of 10. Okay, variability on short time scales, mainly the so-called flares. I will look into detail into flares and how we study them. The problem is, as with everything, the sun is the only star where we can resolve the surface spatially. So it's easy to observe a flare, which is a localized brightening on the sun. As you can see here, the intensity goes up. For stars, we cannot resolve the surface, so we can just see the global average. But we can measure how the brightness changes over time. And this would be the typical time profile of a flare in optical light. It's on the order of minutes duration. Flares are also seen in the corona and X-rays. We'll come back to that in a moment. But let's look first at our standard picture of what we think is going on in a flare. What is happening is that the magnetic field sets energy free when it reconnects to a more energetically convenient situation. And this energy goes partly in particle acceleration and partly in heating. Now the particles are confined to the magnetic field lines, so they flow along the field lines down into the lower layer of the atmosphere, the chromosphere and the photosphere, where they induce a high pressure region, and so the chromospheric plasma moves upwards. It's still confined with a loop, so it actually fills up the top of the loop here, where we eventually have a denser and a very hot plasma that produces X-ray emission. So we have the X-ray flare from the top of the loop, and we have actually a flare in the optical band here when the energetic particles hit the chromosphere. And one part of my studies will be later on to compare this emission in flares during the optical and the X-ray phase. One last part of the introduction, long-standing problem in solar and also stellar physics is the so-called coronal heating problem. The problem is that we have understood more or less how flares work on the basis of the scenarios that I've shown you, but we do not know why the stars and the sun have actually quiescent X-ray emission. That seems to be not variable, right? How this is produced. Now there are basically two possible explanations. This had not been clarified. One is that there are magnetic waves, and the other possible explanation is that there are tiny flares, so-called nano flares, that we cannot resolve in images, but that could provide low-level heating events. And one important parameter to constrain this nanoflare hypothesis is the so-called flare energy frequency distribution. You see it for the case of the sun here. This is the number of flares per time with a certain energy. Okay. And you can see that this follows the same power law of many magnitudes of flare energy. And if you simply integrate up over this power law, you get the total power that is available in flares. And if this index of the power law is larger than 2, okay, with a negative sign here, then in principle you have infinite amount of energy available in these nanoflares if you extrapolate it back. And therefore, this is a critical parameter to measure that in these days we can also measure for stars, as I will show you later on. Okay, so let's move on to the research we are carrying out. I have actually defined several topics. Unfortunately, I think I may not be able to go through all of them. So I will focus here mainly on the first one, the activity on M dwarfs. We study how this activity is related to other crucial parameters of the star, such as rotation, age and mass. We study the physics of the flares, and I will put in a little bit on what we can learn about planets, or how the X-ray emission or the flaring emission of stars can influence the planets. And then I have these additional topics where I go beyond the M-dwarfs into the bottom of the main sequence, into the brown dwarf regime, and where we study in solar-type stars, in particular the activity cycles. And I think I may be able to give you only a very brief outlook on these two other topics. So let's start here and putting the activity of the stars in context with other parameters. It is actually strongly connected to a number of important parameters for stellar evolution. We have already seen that rotation and convection drive the stellar dynamo. The stellar dynamo creates the magnetic field, and stellar activity is connected to the magnetic field. So we have already two ingredients here. It turns also out that activity strongly depends on age. It decreases with age. This is because the dynamo efficiency decreases, and the reason for that is that the rotation period decreases over age. This is the so-called spin down of the stars, which in turn is believed to be due to magnetic braking. So it's a complex feedback loop between all these parameters. An additional important factor is specifically for the activity-age relation, that this is interesting for exoplanet evolution. And all this is mass or spectral type dependence. And the problem with this is that there exists no sample of stars from the observational viewpoint for which we can measure all these parameters together. So in our work, as I mentioned already, we're focusing on the lower part of the main sequence, so we will study the M-dwarf stars. Let me show you rotational evolution models of M-dwarfs. Now, this is not the most recent model here, but I prefer this over many other pictures here, because it does have some data in it, and it shows you the observational parameter with which we measure rotation in stars, which is the rotation period. And you can already see that for M-dwarf, this is only for M-dwarfs, you can see that they can have rotation periods between fractions of 1 day up to about 100 days, and then it gets fairly difficult to measure those. From a theoretical viewpoint, we have here 3 regimes. First, the stars are still locked to their accretion disk. They are not evolving rotationally. Then they are contracting to the main sequence. In this phase, they spin up. And then comes this long phase of spin down, which is very poorly constrained observationally. You do see actually some data points here, but these are not individual age measurements for stars. This is something more globally derived from kinematics and motions in the galaxy. So all these measures are fairly uncertain here. So what we are trying is to set out, as I said, there is no set of stars for which we can observe all the parameters. We try to separately constrain the rotation activity relation and the age activity relation with different samples, and then we kind of tie this to angular momentum evolution and therefore to magnetic braking. And the activity, we can probe it with different types of space missions. The one is in the optical regime, where we probe the photosphere, and in X-rays, we probe the corona. So let me start here with optical photometric space missions, what we can learn. These are Kepler and TESS. And I show you first the wealth of observational diagnostics that we have for activity in such light curves. So on the bottom, you see a typical light curve observed with one of these space missions, and you see 2 typical features. One is this periodic modulation, which is due to the rotation of star spots. So if you have your dark star spot, as in the sun, on the front of the surface, then you have a lower brightness, and when the star spot has rotated behind the star, then you have a higher brightness. And therefore, you can measure here directly the rotation period, but also the amplitude of this variability tells you something about the amount and the distribution of the spots on the surface. If we subtract out this signal, then we have this, what we call the flattened light curve, and you still have these peaks, these outliers, which we can identify as flares. And from the flares, we can also measure detailed parameters like the rise time and decay time and so forth. One very important parameter, or interesting parameter, that we figured out for the first time here is that in this residual variability, after subtracting both rotation and flares, basically the standard deviation of the rest here, we still have some astrophysical signal, as I will show you in a moment. Let me first complete here that we have more parameters that we can measure in flares. We can measure the individual energy just by integrating over the flare light curve, and we can do these cumulative distributions that I've shown you already for the sun, one example. We can do that for stars now as well, and we can measure this power law index. A few words to those space missions. There are actually 2 missions that we're using that have been the most prolific lately. The first one was the Kepler mission, which later was converted into K2 mission. The Kepler observed for 4 years consecutively one given sky field with a cadence of 30 minutes. In K2, we have the same telescope, but it looked for 80 days each on different fields of the sky, and with a faster cadence. And TESS has operated lately, as it came after the Kepler mission, has a very large field on the sky, and it has divided the whole sky in 26 sectors and observed one sector after the other. And it does basically an all-sky survey, except for some parts in the ecliptic here. Okay, let me give you an overview over the samples of M dwarfs we are studying. You don't have to worry about the details here. I just want you to catch that we are basically operating in the regime of early M dwarf stars. So we're barely scratching the boundary where the stars become fully convective. This is a very interesting boundary, actually, but we are not quite able to study it with these samples. And the problem is that the cooler the spectral type, the fainter the stars and the more difficult they get to be studied. Right? So in all our samples, we basically focus on the early M-dwarf stars. One of the first results we got is if we plot all the various activity indicators that I've shown you before over the rotation period, they all follow the same pattern. Quite strikingly, at a period of about 10 days, there is something changing drastically, and that we go from a high activity state to a low activity state. This is the flare frequency, the amplitude of the flare, and these are measures of the variation of the rotational modulation. And it was quite striking to see this abrupt change, which is not explained so far. It is reminiscent of what I will show you later in the relation where you use X-rays as an activity indicator over rotation period, but there it is more gradual. The overall interpretation is, of course, that here you have the younger stars that are still fast rotating, and then the dynamo becomes less efficient, and you have lower rotation and therefore less activity. Now comes this interesting parameter that I've already introduced to you, and we can see that if we plot for our sample of stars this noise, basically, that's left in the light curve, it behaves the same way as the other activity indicators. So we take this, in fact, as an indication that here for the fast rotating stars, we still have some astrophysical signal. It's not just random noise, but we may have actually nanoflares or small and rapidly changing spots that we're not able to resolve in those light curves. This is an example of flare frequency distributions that I have shown you for the sun earlier. How important is this power law parameter? And we measure here typically slopes of about 1.8. Remember, if it's 2 or larger, then we have solved the coronal heating problem. So we're kind of at the boundary here. We cannot really say anything decisive, but it's at least close to being the solution here. We can also see that fast rotating stars, expressed here by the color code, the darker it gets, the faster rotating, have higher activity, flare activity level, right? Each color and each symbol is one distribution for one star. And this is, of course, in the general picture of activity being stronger for faster rotating stars. It all makes sense, but the spread is quite remarkable here, actually. I will show you in a moment one specific star that we can put now on this plot, and which is quite interesting. Let's move on to the second study that we're carrying out, where we will now replace activity in the optical wavelengths by X-rays. So we have to use X-ray observatories. Where are they? Okay. We still need some measure of rotation. This we get only from optical light curves. We use here the TESS satellite, the successor of the Kepler telescope. And we use various instruments in the X-ray bands. XMM Newton and Chandra are the ESA and NASA satellites that have been around for more than 20 years now. Are still quite workhorses, and now we have a new instrument, Rosita, of which I think you have heard only a few weeks ago by the PI, Andrea Merloni from MPE in Garching. I still have prepared 1 or 2 slides for Rosita. I will show you very briefly what's essential for our work here. The important or fantastic thing is that for the first time now we have a partially simultaneous optical and X-ray all-sky survey, and this is really something unique in the history of astronomy so far. Okay, a few words to Rosita. I will be very brief here. It's a consortium-led instrument on a Russian spacecraft. it has carried out, it's 30 times deeper than the previous X-ray sky survey, that's all sky survey that was done with a ROSAT instrument. And it has carried out to date 4.5, that's wrong, it's 4.5 surveys, not 4.5 years of surveys. It is, one survey takes 6 months, I will show that in the next slide, and it has carried out 4.5, and unfortunately now, at the moment, it's in safe mode, it's not observing any longer. Okay, here is what is interesting to understand light curves from Rosita is how it operates. So Rosita is in an L2 halo orbit, and it orbits, it moves across the sky at a rate of 1 degree per day. And this is also the size of the field of view. So any given sky composition during one survey will be in the field for 1 day. During that 1 day, however, Rosita rotates around its own axis. So it will not observe continuously the source, but come back to it several times during its rotation. One rotation takes 4 hours. So on average, during one visit, one survey, the source will be seen 6 times for a short time interval. And you will see that in the light curves that I will show to you in a moment. Some of the instrument characteristics to be compared to others. The effective area, which is a measure of the sensitivity, is similar to that of XMM Newton, and it's 13 times better than ROSAT. You can read that from the figure if you take your time. The field of view of Rosita, of course, is incredibly, it's perfect, okay? It sees the whole sky, and this is about 160,000 times larger than XMM Newton, which is an instrument for pointed observations. And I've shown you here for reference, this is from a work a few years back, where we see the Kepler field. Kepler has already not such a huge field, but each XMM Newton pointing is much, much smaller, 0.5 by 0.5 degrees. Okay. So even covering the Kepler field with XMM Newton is impossible. There's only 6 pointings that cover it. However, the drawback is the typical exposure time to the survey characteristics is very shallow with ERAS. So on an average observation, we have only 1/50th the sensitivity of XMM Newton. But yet, due to the all sky capability, the number of known X-ray sources has already been doubled by Rosita. And now let me come back to our work. The stellar samples have been selected from a proper motion survey, so these are nearby M-dwarf stars. You don't have to worry about the details, but let's just tell you that after validating and comparing this with Gaia data, which gives us the stellar parameters, we end up with about 7,000 stars. Here you can see them on a Gaia color magnitude diagram. Giant stars have been removed. And here on the bottom, you see the sample that comes out. So only about 1/10, even less, of these stars are detected with Rosita. And only 1/4 of the stars which have an Rosita X-ray detection have test periods. And yet, this is a quite unprecedented sample of 150 M stars for which we have X-ray emission and rotation periods. This shows you a diagram which was quite fashionable in the Kepler area. Kepler data, Kepler has measured a huge number of rotation periods, 30,000 or more stars that you can see here as a function of mass. But the problem is the Kepler stars are very faint and distant, so it's very difficult to measure X-ray luminosity, ages, and so forth. And therefore, we got for this nearby sample that I have shown to you, and we have these 138 rotation periods from TESS. TESS has a shorter baseline. We can only measure periods up to 30 days here, as you can see, but we sample that region reasonably well. And now, as I said, we go to these nearby samples, and on the right-hand side, I show you the same plot, but instead of rotation period, we have now X-ray luminosity, and you see also that with Rosita, we measure here a relatively large spread for a given mass with X-ray luminosity. Okay? So since we are going deeper to previous observations, we are seeing a stronger mass range here, a stronger activity range. It's been known historically for much smaller samples that there is a relation between rotation and X-ray activity that has 2 regimes, similar to what I've shown you with this change between active and inactive stars from photometric activity indicators. Fast rotating stars have a constant Lx over L emission, and slow rotating stars have the X-ray luminosity declining with increasing rotation period. And this is what I show you here explicitly for M-dwarf stars. This has been done before for solar-type stars. And you can see the evolution should go, Rossby number is basically a measure for rotation here. The evolution should go like this, right? First you are in this saturated level here, and then as you evolve, you go to smaller, lower activity and longer periods here. And what is quite curious, what we find here, there's a kind of an area where we have few or no stars, and we don't really know what it is, but our idea is that there is possibly a period of fast rotational evolution in which then activity drops quite quickly. So here would have a sort of pileup of the stars, and then they move quickly down the unsaturated regime. Another curious finding that goes in the same line, we have not quite explained here, is if you go to very low mass stars here, we see that there is a gap in which we have no rotation period measurements, although with TESS we are sensible out to about 10, 30 days, we do not see these stars. And this also translates here to the plot where we have now rotation period on the x-axis and X-ray luminosity, this relation that we have a gap here. Okay. And we don't really know what it is, whether it could be an observational bias. In fact, we should see these objects with TESS, right? We are sensitive here, but we don't see them. So here it could also be that there's a quick period evolution, but this is a bit stretching here. We don't have the real answer here. Now, what I mentioned at the beginning, from these rotation activity studies, we wanted to point at how we can find the relation with angular momentum evolution. And to do that, we have combined our observations with published spin-down models. Spin-down models depend on age, but also on mass, so we have to restrict our sample to a narrow mass range. I show you here this example for this mass range, 0.4 to 0.6 solar mass stars. We have done it for others as well. And then we can predict, by combining this to the models, actually how the X-ray luminosity evolves with age. The yellow thing here is basically the uncertainty that we get from all the various uncertainties in the model and in the data here. And you can see that it also depends on the initial period of the angular momentum evolution models. Now, we can estimate that, in fact, for M dwarfs, the onset of the decay of activity takes place only at about 1 gigayear ages. And this is when you compare that to solar-type stars, it's much later. So the M dwarfs evolve their rotation much slower. This is the same thing. I'm showing you now 3 different mass ranges. You can see if you move to lower masses stars, this activity decay sets in later and later. Now, the problem is there are very few observational constraints. I've plotted in a few stars. These are chemokinematical ages, okay, no direct age determinations. And these are open clusters, but we have no open clusters beyond 600 million years. The higher this age, and therefore it's very difficult to constrain these models by observations. So a few years ago, actually, I went along and thought a quite clever strategy. It's moving quite slowly, this project, but it would be nice to have a direct age determination for a given star. And we can get around this problem. If you observe an M dwarf, which is a binary with a white dwarf, then the white dwarf ages are reasonably constrained from evolutionary and cooling ages. We assume the system to be coeval, and then we have the age of the M dwarf. The problem is these systems are not abundant. There's not so many known of them. We've observed a couple. You see here one example here. The white dwarf, by the way, is not an X-ray emitter. It's an evolved dwarf. It's quite cool, the A dwarf. And here you have the first results. Now, it may not seem so spectacular, but it actually starts to mimic what we're actually seeing in solar analog stars as well, that there is some decay of the X-ray luminosity with age. And now we can use that to calibrate the models that I've shown you earlier. Another interesting feature, now we have for the first time an X-ray temperature. We can measure from the spectrum in X-rays the temperature of these stars, and these are our data points that we're adding to other observations in which the age of the star is not known. This is all work in progress. What is this good for is that the exoplanet community is actually studying how X-ray emission of the star influences planet atmospheres. I will say something about that in a moment. And it's very useful for them to know both the flux of the star and the temperature of the X-ray emission. Let me come to my second topic, a combined X-ray and optical view of M dwarf flares. What is known about it? Very little. There are only basically 2 studies where we have simultaneous flare observations of stars with XMM Newton and one of the photometric space missions. And we have put those together, selecting only the M dwarf stars. This is the sample that you have. And we can make a correlation between the energies that you see in the X-ray flare and the energy that you see in the Kepler band in the photometric optical flare. What we are doing in the next step is actually we're using observations from TESS. Okay, TESS is similar to Kepler. We have more TESS data. So what we want to do is to calibrate or construct, synthesize flare frequency distributions in X-rays from test data. And therefore, the Kepler data is, well, not so useful. We need to know the flare energy in TESS and what we can say about it with relation to flare energies in X-rays. So let's first look at a comparison between Kepler and TESS. These are the photometric filters. The Kepler filter is much bluer than the TESS filter. And a typical flare emission has a black body temperature of about 9,000 Kelvin. So one would expect that Kepler measures a higher flare energy than TESS, right? Because it's more in the region where the flares are bright. However, what we observe, this is one of very few examples of a star that has been observed with both missions. We observe that the flare frequency distributions, okay, the power law story here, is basically indistinguishable between TESS and between Kepler. And therefore, both energy bands actually measure the same amount of energy. The reason is, the likely reason, that the TESS filter is just so broad that it covers a broad wavelength range and it makes up for the fact that it's in the not so favorable spectral region. And now we have used this actually. Well, what is the trick is then that the Kepler energy is equal to the TESS energy of the flare, and we have this calibration that I've shown you here between X-ray and Kepler flare energy. So we can use our observed distributions of flares with TESS that are shown here in black, and we can synthesize what is shown in red, the X-ray flare energy distributions. Okay. Now this is the first attempt to do that, and we have to prove that by observations. Right now we do not have the statistical database for flares to verify whether these predictions are reasonable. This is the next idea. Let me show the steps that we're doing towards that. We have, for the first time, as I pointed out, an all-sky survey in optical and X-rays that is partially overlapping in time. And the great thing is that we have an area near or around the ecliptic poles, which is deeply exposed by both out-sky surveys, because the sky is a sphere, right? And therefore, by definition, if you scan around the pole, you always hit the same region, basically. So we can make use of that, and we have selected M-dwarfs that are specifically located here at the ecliptic poles because they have long light curves in both instruments. And I show you here only initial results from a master thesis that's ongoing here. TESS, the optical light curve in blue, the rotational signal, and they have here flares superposed, and in A Rosita X-rays we also see flares here. There are two more examples where I show you only the A Rosita light curve here to point out that there can be very long flares. We do have TESS data, but it's a bit confusing. What I'm pointing out here, that many of the stars in A Rosita, we discover them only because they're flaring. Okay, here they're at a count rate of 0. No photon is arriving for a long time, and then you have a huge flare. And here, a similar example, and we have a huge variety of flares, which we are struggling still to understand, but it's really quite exciting because for the first time we have now a statistical database of simultaneous optical and X-ray flares. Now, the cadence of A Rosita, as you have already seen, is not that great. I show you here, this is a prototypical flare star, AD Leo, early M-dwarf star, the example of a flare star, nearby at a distance of 5 parsec only. And you see here two light curves in X-rays that have the same duration, roughly 1 day. A Rosita on the left, and this is a pointing with XM and Newton, and you can appreciate the difference, of course. You can also see that AD Leo is not near the ecliptic poles, it's near the ecliptic itself, where the exposure is very shallow. You have only 5 visits by A Rosita instead of the long light curve that I've shown you before. So we are currently quite excited. I'm showing this for the very first time, actually, about this, what we have called the great flare of 2021 of AD Leo. We're actually still evaluating the energy in this flare, and maybe you know, if you're familiar with this topic, about an energy of 10 to the 33 ergs. In total, it is called a super flare. So we're kind of at the boundary here. We're still getting the right number, and then we can call it a super flare or not. What do we expect if we, well, I should say we have simultaneous TESS coverage of that flare. I'll show you in a moment. And what would we expect to see from this simultaneous TESS optical and X-ray observations? Let's think again about the standard flare scenario. Okay, you have first the particles traveling downwards, and they will produce an optical flare here in the legs of the magnetic loop, and then the plasma moves up and produces an X-ray flare. And this is known from the sun. This has been observed. You have actually third components that we are not able to observe in stars. These are hard X-rays. This is directly this gyrosynchrotron emission from the particles that are spiraling downwards in the magnetic field. And this has a rather similar temporal signature to the so-called white light flare, which is what we can also measure with Kepler and TESS, as I've shown to you. And then you have the signal from the soft X-rays from the top of the coronal loop that actually has a time lag here. And this is expected because of the sequence of events that make up the flare that I've explained to you. And this is now, again, our great flare on Adilio. On the right-hand side, you see on top the X-ray light curve, and at the bottom the TESS light curve, and we're just working on this right now. You see, in fact, I have marked with a vertical line here the peak of the TESS light curve. We can measure a delay here. And another interesting feature, I'm comparing this again to a solar flare on the left-hand side, is that is what is called the so-called Neupert effect. If you take the time derivative of the X-ray measurement, dLx over dt, this is shown, I hope you can see it, with these open symbols here, and I show it again here. This has more or less the same temporal sequence as the white light flare. This was predicted more than 50 years ago, actually, by Neupert. Or it was actually observed on solar flares, not predicted, but the explanation was then just this temporal sequence of the center flare scenario, that there is first the optical flare that actually then gradually fills the loop, and therefore more and more X-rays get produced over time. And it's also shown on the left-hand side for a prototypical flare in X-rays, where you have here this derivative of the Lx over dt. Okay, I think I'm almost at the end. Let me come to some exoplanet. Oh, no, this one slide. Okay. Now, you have seen this slide before, the flare frequency distributions for M-dwarf stars, and now we can fit in AD Leo. Now, AD Leo, we have observed actually only 4 flares with TESS that are shown here in red. It's red because this traces the rotation period of AD Leo. It's a fast rotator. It's the same color as the fast rotating M-dwarfs. And it was at the beginning quite disappointing. The problem is this TESS light curve is terribly contaminated by a nearby star of, I think, 1st or 2nd magnitude, Gamma Leo. So we had really trouble actually cleaning up the light curve. And the great flare that I've shown you in detail is actually this one. It's not even the largest one that we see here. Now one would wonder, why do we have a much flatter slope here? The point is actually due to the high noise in the light curve, we are not complete to the detection of flares, even of the size of the great flare. Okay, so we would probably have to, here we are complete, we have to move up, basically, correct upwards these flare frequencies, because simply we are not sensitive due to the noise in the light curve. So what we have, I said maybe it's a super flare, we actually still have to calculate the bolometric energy, okay, and that could quite well be above the critical limit of 10 to the 33 of making it a super flare. And super flares are a lot around in the literature, therefore it's exciting to have one, but it doesn't really matter whether it's factor 2 lower or not. Okay, some exoplanet-related stuff. Let me fit in. Let me first ask the questions that we have. The major interest of the exoplanet community lies in these 2 questions, that the stellar high-energy radiation could affect the composition of planet atmospheres. This is the topic of photochemistry. It has not obtained so much attention in the literature so far. The more studied is the so-called atmospheric escape or evaporation of the planet atmospheres because of the irradiation by the star. I show you now 2 pieces of where we can contribute with our work. But first I have to show you the theoretical background. So for the question 1 regarding the photochemistry, there is this seminal paper. There was a previous one as well, where they have actually calculated how the chemical reactions in a planet atmosphere change due to the flaring of the star. And in particular here, the focus was on the ozone content of a putative planet atmosphere. And what they have calculated, they have used some kind of realistic flare distribution extracted from the kind of observation that I've shown you. And they show here on the left-hand side how the change in the ozone layer depth changes over time if you have this illumination by flares. These are flares of different energies here. And what you can see on the left-hand side, yes, the ozone layer reduces by not very, very much, only by 1%, and then it goes back to the base level. Now, if you put in an additional component of flares that I've not yet talked about, that is that there's also a particle flux, then these calculations predict that the ozone layer for some time can actually be almost completely depleted. So apparently for this effect of photochemistry, it's not the radiation, but it's the high energy particles that are important. Another problem is that on stars, we cannot measure the high energy particle flux. But what one can do is actually for the sun, in this paper, this was calibrated for the solar proton flux as a function of X-ray flare intensity. And there were different parametrizations that give rise at high energy flares of very large uncertainty, unfortunately. Now, they have actually put in some observed stellar flares, but one must say none of those was actually observed in the X-ray band that is shown here. So this involves complicated calibrations between optical and ultraviolet flares, which were not so well known here. And now comes because why it's important to have observed this large flare on AD Leo. This is the first time that we have, well, I should explain the GOES class. I don't have a lot of time. GOES class is a measurement for the X-ray flux at the peak for solar flares. There was a GOES satellite who measured in a wavelength of 1 to 8 angstrom. And this goes up to an energy of about 12 keV. It's a rather high energy, and you can measure that only if you have a very sensitive observation. And with the AD Leo flare, we were able actually to constrain to measure this GOES class. It's an X1300 flare, so it's located about here on that scale. And we are able basically to predict, although in a rather large range here, the proton flux related to this event. And this, I'm quite sure, the people who are doing this kind of models will be interested in this kind of information. Okay, I think I do not have so much time. I have a few more minutes. Okay, sure, a few more slides. Okay, again, flare energy frequency distributions. Okay, we have seen several of those. Here I show you another sample yet of M-dwarf stars, and you can see here again we measure the indexes. We are close to this critical limit for the coronal heating, but there is more to it. There have been people who have actually defined regions in this diagram where flares become important for exoplanets, and there are two features here. These are shown on the right-hand side here. One is that there are calculations that, according to this law here, if the flare frequency is larger than this law predicts here, where E is the energy of the flare in the U band, then you can actually trigger prebiotic reactions. That is, you can drive chemistry that creates life from non-life. Okay. This has been predicted in that paper. I'm not citing it here, Remark 2018, and transformed in this form here. And this would be actually, for each flare, this has to be calculated separately, right? Because there's the flare energy in here, and for our flares, this translates to this region, okay? Which we are not quite reaching. Our flares are fainter than this limit. So our flares are not bright enough to trigger this important prebiotic chemistry, according to these models. And the second thing is, again, the ozone layer depletion from the paper that I've shown you earlier. They considered that you also need a certain flare frequency above a certain energy, which is shown here as the orange range, in order to deplete the ozone layer. And we're not reaching that either with our flares. Okay? The typical M-dwarf flare is neither bright enough to trigger this prebiotic chemistry, nor is it actually destroying an ozone layer if it's there. So contrasting effects on planets. The second topic was the atmospheric evaporation that you show you very quickly. Very many people are working on that, actually. This is, again, the theoretical background. So if you do models of the thermal evolution of a planet and you combine that with mass loss that is driven by the irradiation from the star, then you come up with a story like he is shown here from these hydrodynamic models, a mass loss as a function of age. And as you can see, this is actually reminiscent of the X-ray luminosity versus rotation and age plots that I've shown you. So before the star is in a saturation level, and then there is a stronger decrease here. So these kind of models require as an input how the X-ray luminosity changes with age, like I've shown you before that we have calibrated. Okay, what they did actually at the time, okay, it's not so important. They used this poor data here just to show you how much more data is there around now, thanks to Kepler and TESS and Erosita. And now this is one of the recent works where we have applied this nearby star with M-dwarf star with a planet. And here you saw what was yellow in the previous slide is the bluish curve here is our predicted X-ray luminosity over age relation. This is combining with the angular momentum evolution model. And in gray, you see actually a prediction which is purely empirical based on Pleiades, Hyades, and I think Proxima Centauri. Oh, well, where's Proxima? Yeah, could be. Okay. So you can see that the model that we're using actually predicts a somewhat slower evolution than this purely empirical law, but the empirical law is based on just 3 points in time. What we've done for this star with a newly discovered planet, we have obtained a very deep observation with XMM Newton, and we have figured out that it's an extremely low X-ray luminosity. It's down here, from which, according to these laws, we can predict an age of at least 5 gigayears. And now you can combine this with these models of photoevaporation, and you can actually backwards reconstruct the evolution of the planet atmosphere, and you can predict what was the maximum mass of the atmosphere that it could have had initially before it eventually evaporated, right? It turns out to be 38 Earth masses for this planet. Today, the planet has a virtually, well, a very, very tiny atmosphere, as you can see here from the radius over mass plot here. These are the different estimates for radius and mass of this planet, and that it turns out to be Earth-like with maybe a tiny atmosphere, okay, but nothing in terms of Earth mass or several Earth masses. Okay, and now I would come to my last topic, and I think I was quite aware that I don't have time to show it to you, so I've prepared just one slide in which I give you a brief overview over activity in different mass regimes and how we are studying it. First is the bottom of the main sequence, and second are solar-type stars, but I've squeezed it all into one slide here. The first one actually connects to what we have learned before about X-ray luminosity as a function of spectral type. We have studied this regime of early M dwarfs. Okay. Now, if you go to late M dwarfs, they're also called ultra-cool dwarfs, you have much fewer data. And if you go into L dwarf regime, we are now bridging the regime to the brown dwarfs, which are not hydrogen burning anymore, but this shouldn't matter for activity. There are actually only 2 detections. Okay. This one has 4 photons detected with the Chandra satellite, and this one we have discovered serendipitously, one can say, a super flare. Now, this super flare, in fact, has an energy larger than 10 to the 33 ergs. It's not observed in this detail because this star is very distant, and we observed it in, by chance, this had an extremely long observation with XMM Newton, where it turned out to be one flare and nothing else. So this was actually a science story because it's a very bright X-ray flare on an L dwarf. And the other topic, something completely different. Here we are studying actually or searching for X-ray cycles in solar-type stars. This is Epsilon Eridani. It's a young kind of solar-type star at an age of about 500 million years. And we can see in black here chromospheric S-index measurements where this cycle had been detected in the 2010s. It's a cycle that has a period of only 3 years as compared to the 11-year cycle of the sun. And in fact, with the red, the X-ray measurements, we are finding the same kind of variability. Okay, there's much more behind that project. Actually, we have done that for 3-4 stars. And it turns out if you go even younger, then you have no cycles anymore. This actually has already a cycle amplitude of only a factor 2, as you can read here from the flux measurements. I've shown you for the sun it was at least a factor 10 or so. What we think what is happening, the younger stars have more active regions on the surface. At a certain point, even in the minimum of the activity cycle, they're completely covered with active regions, and you just cannot add any more, and therefore you do not have the cyclic variability. And we're actually doing some interesting modeling, trying to infer indirectly what kind of magnetic structures we have on the surface of this star using observations from the sun. But that's way too much for this talk, and therefore I think I should stop here. And you may know my train is in about 1 hour, so I'm very happy to take your questions, but not for 1 hour. Thank you.
Thank you very much, Beate. What a gold mine you struck here.
Sorry.
What a gold mine.
Yes, too much data.
Here with,
but I think everybody has this problem, yes.
The X-ray activity. I'm sure that there's going to be a lot of questions. I suggest if people online would like to at least indicate in the chat that they want to ask a question or actually write the question in the chat. That's probably the most reliable way. In the meantime, I don't see anything right now, so do we have questions from the floor? Yes, Keith. Sorry, yeah. You should speak.
Yeah, very, very interesting work. I have two small questions. First of all, I didn't really understand why the prebiotic chemistry would depend on the frequency of flares.
What, sorry?
On the frequency of the flares. That's what.
Yes, it does depend.
I mean, why would a chemical reaction depend on the frequency, not on the total amount of X-ray
well, on the
particles?
frequency distribution with flare energy, basically. That means how often you have a flare of a certain energy. Of course, if you have more often a flare of this, basically this power law, right?
Right.
So if it's less steep or steeper, then you have more energetic flares, which have a larger impact on the chemistry.
Yeah.
Of course.
Well, it sounded to me a little bit like as if there is a cutoff.
I was not explaining it very well.
Okay. And then you mentioned it at the very end a bit about the cycle. You know, the sun has this 11-year cycle, but you also mentioned the saturation of the activity for very high periods, right? And somewhere at the beginning.
Small periods,
Small
fast
periods.
rotation. Yes.
Exactly. Do I understand correctly that even in the saturated regime, you do see that if you go to shorter periods, that also the period of the cycle gets shorter until it's completely
No, yeah,
vanishes?
very good point. I don't have that figure, and it's not published yet, but you have actually, if you go this X-ray luminosity versus period that I've shown you earlier here, for example here, right? So all the stars with known X-ray cycles are actually in this regime here. And I have not shown the plot, it's too bad. Yes, I should show it, it's not published yet. And there's also a sequence in H, more or less. Okay? So we have only about 8 stars with known X-ray cycles. Many of them are old, several giga-years old. One is Epsilon Eridani, 500 million years, and another one which is 200 million years. And Epsilon Dani is about here, and the 200 million, so there is a sequence here, basically. So in saturated stars, it seems to be consistent, right? There's no activity cycle in saturated stars.
Beate, very interesting. Thanks for this illuminating talk. I'm wondering about pre-main sequence stars and their activity.
Yes.
Because they also do have activity, they are probably fully convective and so on and so forth, but they should not have had time to build their own magnetic fields. So it's probably frozen in from their collapse. Can we learn something about then the magnetic fields in the cloud before that, or would you
Frankly,
argue
I
they built
don't
up
know
their own?
if they, I mean, pre-main sequence stars on the order of a few million years. I never thought about that, but I had no time to build the magnetic field.
I would assume, no? Or would the dynamo be fast enough? Would the internal dynamo
I
be
don't
fast
know.
enough?
It's a good question. Yes, I never thought about that. They could have. Why would they not have a dynamo? I mean, as soon as you have, if you go to fully convective stars, for example, on the late main sequence, right, you have only convection. You're supposed not to drive a solar-like dynamo, which needs the radiative zone in the interior, so you have some convective dynamo. And I think that could operate in pre-main sequence stars.
And that would be fast enough to build enough magnetic to explain.
I don't know, frankly, but I think so. I don't know. But I can show you one. I don't have a lot on pre-main sequence stars, but what is quite curious here, I've shown you this plot earlier on the left one. We can compare now the X-ray luminosity as a function of mass in the M-dwarf regime to what is observed in younger stars, Orion Nebula, for example. And in fact, they turn up to have higher X-ray luminosity. Everyone can think, okay, these are faster rotating. Then it makes sense. But what is quite curious here, these stars are very young. Many of them are accreting. And actually, it turns out if you do Lx over L-ball, the typical saturation level actually is lower for Orion. So you have to consider that as well, that you have accreting stars where magnetic activity seems to be suppressed somehow, maybe by the accretion streams. So, but that, your question, I cannot really answer it, but I will think about it. Yeah, thanks.
Okay, thank you. We have no questions from Zoom at the moment, so next question from the floor, Wolfgang.
Yeah, so question about the size scales of flares. You showed the solar image in the beginning, the size of the flares, and you mentioned nano flares, and you showed also AD Leo and the super flare. So for the nano flares, is there a smallest size scale which depends on, I don't know, size of granulation or characteristic size of a flux tube? And for AD Leo, the time delay between optical and X-ray.
Yeah.
Does this give you a size scale? You showed the image.
No, I think you cannot use that to do the size, or it has not been done. But what you can do, actually, we're working on that as well, concerning the size. You can determine the flare loop size if you combine the observed parameters, which is the temperature and the density during the X-ray flare, to hydrodynamic models. We're working on that right now. Then you can extract more or less the length of the flare loop. And it turns out to be on the order of 10 to the 9 centimeters. Okay, so factor 10 to 100 smaller than the sun. But in fact, I think the image that I've shown you at the very beginning, this was really a tiny flare, right? I actually don't know if this looks very small. Despite it's smaller than the spot even. Yeah, yeah. There was another component to your questions. I don't.
The nano flares.
The nanoflares, yes. I mean, the nanoflares are not even on the sun seen spatially, right? They're not resolved. So what you measure is the energy, a small flare in terms of energy. I'm not sure how easily you can scale that back to the size.
Thank you.
Okay, still nobody from the... there is a question, Brian Reville. So, Brian, do you want to try and communicate verbally?
Yeah, can you hear me?
The physics of the flare.
Hold on a second. Try again.
Yeah, can you hear me now? I was just curious, what determines alpha in this equation here on the screen?
What determines alpha on the screen?
I don't think there's a thorough physical theory behind that. Okay? It's just that flares are stochastic events, and therefore the smaller ones are more frequent than the less. I think it's an empirical law, as far as I know.
If I may ask a question myself, I think there's still time for your train. We've got
Yes,
lots
I
of
think
time. As far as I understand, you've done that sort of cross-correlation. You've taken the X-ray source catalogue and you've looked for optical sources nearby, and you've found this sample of 150-ish associations between the X-ray.
This one here? Yeah.
So my question is, are you sort of biased towards flaring sources with that sort of technique?
Well, yes, definitely. I mean, in the later study than what I've shown you next,
yeah.
This is, of course, we are studying only the active stars, yes.
Right.
So we did it actually the other way around. We started from an optical catalog. We start from an optical catalog and look for X-ray sources. And only 10% or less have detections in X-rays. The other ones are too faint.
And were those optical sources, the fast rotators, you try to give yourself the best chance?
I think the optical sample is, well, it's also a bit biased in terms of distance, as you can see here, but we're only small distance, but this should not be biased with respect to rotation, right? Rotation does not influence the optical brightness.
Right, but I'm not familiar with the optical catalogs, but can you select a sort of sample of
we're doing that actually,
and stack them up and then see if there's any X-ray steady state there?
We are studying a subsample of these stars. This is just a complete proper motion survey of the sky with 9,000 stars. I've extracted all the stars in 10 parsec. And this upgraded with Gaia, there is a complete Gaia census for all the stars in 10 parsecs. So we think we have to do a volume complete sample there, right? And we start to study the X-ray emission of those. And it turns out that even in this volume complete sample, only about 60 to 70% of the stars are detected in X-rays. So everybody thinks stars are easy. We know all about stars.
No.
Not even about the most nearby stars, we know the X-ray emission levels. And of course, I think we do have biases here, for example, in this diagram, right? There could be something down here that we're not measuring yet.
Yeah.
And the same, in fact, with A Rosita here, we are seeing some remarkably faint stars. This is quite a puzzle. We don't really know what's happening here. Fast rotator should be bright in X-rays, right? And we didn't see these stars down here before. But
fascinating. And I note that the 10 to the 29 ergs from your fast per second from a fast rotator. I mean, if they continued that through their lifetime, galaxies will be very, very bright as a whole in X-rays. I mean, that's, you just multiply 10 to the 11 by 10 to the 29, you get a large number.
Yes.
In other words, stars have to decrease in X-ray luminosity fairly rapidly. Otherwise,
I haven't thought about that.
well, this is just numbers in the head, but it does look like a very large number, this 10 to the 29 from individual stars. Anyway, that's completely fascinating. I'm looking to see if there's anybody online. Okay, no, I don't think there was anything anything new as far as I can see. So I think we'll just gradually. Oh, one more question. Train's still waiting. Long time.
It'll be delayed. Yes. You're going to laugh because I forgot my question, but I know it's on page 40.
Oh, 40. 40? Okay.
Yeah.
I also forgot what is on page 40.
Yeah.
Ah, this nice one. Oh, okay.
Right. Yeah, no, I remember my question. It looks as if the flares in ERAS are
Eurosita survey, yes.
are not at the same position where the flares in TESS are, except for that one. But in the other one,
Yes.
if you go
Yes.
earlier, there is
Yeah,
two.
there's
that
no
are
X-ray flare.
exactly.
Yes.
Are they?
I have no clue. I'm quite surprised, okay?
Yeah.
So what is observed in the sun actually only, depending on the study you're looking at, between 50 and 80% of the X-ray flares have an observed associated white light flare. And even for the sun, they don't know if there's something in the physics that there is not always a white light flare associated with an X-ray flare, or whether it's observational bias.
And vice versa.
And vice versa.
Yeah.
Yes, this is very strange here. We have a white light flare without an X-ray counterpart.
Yeah.
So we don't have, actually there's a variety. These light curves are really crazy, okay? They're really great to see, but they're not easy to understand. And the only thing, the obvious thing I can imagine, there was a short event in this gap here, okay? Because between one data point and the next, with Eurosita, it's about 4 hours, and the X-ray flare could have lasted 1 hour, in principle. So we are not seeing all the events here. But still, it's really fantastic data.
Right, well, thank
Okay.
you. Thank you again for the question and the discussion. Final remark, I think it would be so interesting for a lot of people working in high energy astrophysics if you could scale up the demographics of the X-ray emitting stars to this third component you can't see directly, which is the energetic particle
Yes,
component.
but I think there's no chance. to
No,
measure
but I
these
mean,
on stars.
at least
Yes,
using
yeah.
the solar calibration, just
Yeah.
to see what sort of numbers come
Yes,
out for
yes.
the total injection rate of high energy particles.
But as you have
Within
seen, even
stars, at
these
least.
calibrations based on solar observations have a huge uncertainty here, right? That predict these
Yeah, but
extrapolations.
you
It's
know,
crazy.
it's still a fun number, you know.
Yes, yeah, sure.
Okay, I don't see any more questions either online or in the hall, so I think it's now almost time to give our thanks once again to Beate. But before I'd just like to make an announcement. Yes, it's working this time. So that's it. So the first announcement is that next week we're on holiday for Pfingsten, so there won't be a colloquium. In 2 weeks' time, we will return here to hear Rainer Schödel talk about these amazing new surveys of the galactic center region and what they mean about physics processes in the interstellar medium and in the stellar populations in the galactic center region. So we look forward to that. And now I'd just like to once again thank Beate for such an intuitive and informative talk, and it's certainly going to be very interesting to see what happens in this fascinating area from you and your team in the future years. So thank you very much indeed, Beate.
Thank you again. Thanks.